All right, get ready because today we're going deep, really deep into gravity itself.
Deeper than a black hole.
Maybe even deeper. We're going to be talking about a solution to Einstein's equations, a solution that seriously changed how we see the entire universe.
A pretty big deal then.
Huge! And the guy who figured it out, Karl Schwarzschild, did it while serving on the Russian front in World War I. Talk about a high-pressure environment.
Yeah, not exactly the quiet lab you'd picture for groundbreaking physics work. His dedication is incredible.
Absolutely. So today we're going to try to understand exactly what Schwarzschild figured out and why it still matters so much, even over a century later.
Well, to really get Schwarzschild's breakthrough, we kind of have to start with Einstein. His theory of general relativity, total game changer for physics. But even Einstein had trouble finding exact solutions to his own equations about gravity.
So it's like he gave us this amazing puzzle, but without all the pieces.
Exactly. His field equations, they tell us how matter warps space-time, how it creates gravity, but they're insanely complex to solve. Like, imagine trying to predict every ripple in a pond after you've thrown in, 100 pebbles all at once.
Okay, yeah, I'm starting to see the mathematical mayhem here.
Yeah.
So 1915, Einstein lays it all out, throws down this challenge to the whole scientific world.
Right. Find a way to make sense of these equations, apply them to the real universe. That's where our guy Schwarzschild comes in.
Hold on. He's in the army, middle of a war, and solves what stumped Einstein. This guy was operating on another level.
Seriously. So 1916, Schwarzschild sends Einstein a letter. It's got this elegant solution to the field equations, describes the gravity around a single, non-rotating spherical mass.
Sounds kind of simple when you say it like that, but I'm guessing it's anything but.
Oh, you're right. It's like finding a perfect snowflake in a blizzard. Pure order in the middle of chaos. And the implications. Huge. This helped us understand gravity in a whole new light, literally.
Okay, you've got me hooked. So what did this solution actually tell us? How did it change our view of gravity?
It gave us this precise mathematical way to describe how space-time is curved, warped, around a massive object. For that, we need the idea of a metric.
A metric. Sounds like sci-fi jargon.
In a way, it is. Think of it like a special ruler, one that can measure distances and time in this warped space-time fabric. It's like a measuring tape that bends and stretches along with the universe.
Okay, I can kind of picture that.
Yeah.
How's it work in practice, though?
The Schwarzschild metric, it's what we get from his solution, tells us exactly how to measure these distortions, like a map showing how much gravity is pulling at every point in space and time around, say, a star.
So going back to that trampoline analogy, we can measure not just the dip the bowling ball makes, but the slope, how it changes as you get closer.
Perfect analogy. And understanding how space-time is curved, that lets us predict how stuff moves under gravity's influence. From light bending around a star to the exact path planets take in their orbits. Really powerful stuff.
My brain's starting to bend a little now, too. So Einstein, he had this general idea, but Schwarzschild gave us the way to actually measure it.
Precisely. Before, Einstein only had, approximate solutions. They worked okay for weaker gravity, like around our sun, but that's it.
So Einstein had the sketch, but Schwarzschild gave us the high-definition picture.
You got it. And the amazing thing is that this solution, pure math, it confirmed what Einstein had predicted about starlight bending. Even explained that weird wobble in Mercury's orbit.
Wow, two totally different paths, same conclusion. Must have been a huge deal for physics.
It validated Einstein's theory and cemented how important Schwarzschild's work was.
All right, we've got Einstein's theory, the challenge to solve his crazy equations, and then Schwarzschild just swoops in with this elegant solution. What happens next?
Buckle up. Remember Kepler's third law from school? The one about how a planet's orbit relates to its distance from the sun.
Vaguely. Something about squaring the period and cubing the distance. It's been a while since high school physics.
That's it. Well, using Schwarzschild's solution, we can create a relativistic version of Kepler's third law. Think of it like Kepler's law got a serious upgrade.
A relativistic upgrade. So Newton and Kepler were wrong this whole time.
No, not at all. Their laws work great for most cases, like planets in our solar system. But around super strong gravity, like black holes, we need Einstein and Schwarzschild.
So, like having a regular map works fine for your neighborhood, but if you're climbing Mount Everest, you need one showing every little detail of the terrain.
Spot on. Thanks to Schwarzschild, we now have that detailed map for gravity itself. Lets us figure out how things move around even incredibly massive objects, the kind that are so dense, light can't even escape.
Wait, are we talking black holes now?
We are indeed. And that's just one example of how Schwarzschild's work set the stage for modern astrophysics, our understanding of some of the craziest stuff in the universe.
Okay, I'm officially on board. From math problems to black holes, all in a few minutes. This deep dive is living up to its name.
And we're just getting started. Plenty more to explore.
I can tell. My head's already spinning with questions. But before we get too far ahead of ourselves, maybe let's give everyone listening a minute to catch up.
Good idea. We'll be back in a flash. And we're back. Ready for some more cosmic adventures. Because we're about to head into a realm where gravity gets kind of trippy, messes with how we even see the universe.
Oh, I'm ready. Trippy gravity sounds right up my alley. What are we talking about here?
Gravitational lensing. One of the coolest ways Einstein's theory shows up in the real universe, and it's all thanks to Schwarzschild's solution.
Gravitational lensing. Okay, I've heard the term, but honestly not sure I really get it.
Picture this. You're looking at a galaxy super far away, billions of light years distant. That light's been traveling for, well, billions of years to reach us. But on the way, it passes by something massive, like a huge cluster of other galaxies.
So the light from that far-off galaxy on its way to Earth hits this, what, like a cosmic roadblock?
You got it. But instead of blocking the light, this massive thing acts like a lens. It warps space-time around it, and that bends the light coming from the distant galaxy.
Hold up. Gravity is literally bending light like a giant magnifying glass in space.
Exactly. And that bending can create multiple images of the same galaxy. We can actually see the same galaxy multiple times in different spots in the sky.
Whoa, that's some serious cosmic magic. Seeing double thanks to gravity. My mind is blown.
It is pretty wild, and it's not just multiple images either. Gravitational lensing can distort a galaxy's shape too, stretching it into arcs or even making rings of light. Einstein rings, they're called?
Einstein rings. Okay, now you're just showing off. But seriously, if we can see these things, that means Schwarzschild's solution. It's more than just theory, right?
Absolutely. These observations are like proof positive that space-time is warped, just like Einstein said. And Schwarzschild gave us the map to describe it.
So not just equations on a chalkboard anymore. This is real, observable stuff.
Exactly. What's even cooler is that by looking at these gravitational lenses, we can learn a lot about how matter is spread out in the universe. Even that mysterious dark matter.
Wait, you're saying gravitational lensing helps us study dark matter? That stuff that makes up most of the universe, but we can't even see it.
You got it. How much the light bends tells us how much mass is there, even if we can't see it directly. It's like using gravity itself as a detective tool.
Never thought of it that way. So by watching how light bends around these huge objects, we're kind of mapping the invisible stuff holding the universe together. Schwarzschild really opened up some wild possibilities.
He did, and all this leads us to one of the most mysterious objects his work predicted. Black holes.
Black holes. Now we're talking cosmic legends, the ultimate vacuum cleaners of the universe, sucking up anything that gets too close.
They definitely have that reputation, and Schwarzschild's solution was the first to describe them mathematically.
So even before we had telescopes powerful enough to see them, his equations already said they were out there.
That's the power of theoretical physics. His solution showed that if something was dense enough, it warped space-time so much, not even light could escape.
Okay, trying to wrap my head around that one. If light can't escape, does that mean we can't actually see a black hole?
Exactly. They're invisible to our telescopes, but we can detect them indirectly. We see their effects on stuff around them.
So kind of like knowing a storm's there, even if you can't see the wind. You see the damage it does.
Perfect analogy. We can see stars whipping around super fast like they're orbiting something massive, but there's nothing visible there. Only explanation. A supermassive black hole we can't see directly.
Okay, that's both terrifying and amazing. But how do we know black holes actually exist if they're invisible?
That's the question that puzzled scientists for decades. The answer: a mix of careful observations, tons of calculations, and yep, you guessed it, the foundation Schwarzschild laid.
This is all incredible. Feels like we've taken a whirlwind tour through the weirdest parts of the universe. And it all started with one guy, a math solution, over 100 years ago.
It shows you the power of human curiosity and how a single discovery can change our understanding of the cosmos. And believe me, there's a whole lot more to discover.
Oh, I bet. My curiosity is definitely piqued. But maybe before we go too much further down this rabbit hole, we should let everyone listening take a breather. We'll be back in a bit to explore even more of the mind-blowing implications of black holes and the mysteries they still hold for scientists today. And we're back for the final leg of our deep dive into the world of Karl Schwarzschild.
From World War I battlefields to the edges of black holes, it's been quite a journey.
Before the break, we were getting pretty close to those cosmic abysses, those black holes. You hit it at some even more mind-bending stuff. I'm ready for it.
All right, let's talk about one of the most brain-twisting concepts in physics, the singularity at a black hole center.
Okay, singularity. Yeah, that word definitely sounds ominous. What are we dealing with here?
Imagine the very heart of a black hole. All that matter, everything that's ever fallen in, crushed into a point so small it's basically zero size.
Zero size, like infinitely tiny. That's hard to even picture.
It is. That point, the singularity, is where things get crazy. The density of matter, the curvature of space-time itself, it all becomes infinite.
Infinite density.
Yeah.
My brain just went offline. And if physics breaks down at a singularity, does that mean we can't ever really know what's going on there?
That's one of the biggest mysteries physicists are grappling with. Our current understanding of physics, it just doesn't work at a singularity. It's like our tools hit a wall. We need a whole new set of rules to understand what's beyond.
Like reaching the edge of the map and it just says, here be dragons.
Exactly. It forces us to push the boundaries of knowledge, come up with new explanations. To really grasp singularities, we probably need a theory that combines Einstein's relativity with quantum mechanics, a quantum theory of gravity.
Quantum theory of gravity. That sounds like the holy grail of physics, right?
It is. Unifying those two fundamental theories, that's the ultimate goal for a lot of physicists. And who knows, maybe the seeds of that future understanding are hidden somewhere in Schwarzschild's work.
So his work isn't just about understanding the universe we know. It's a stepping stone to things we haven't even discovered yet.
Precisely. Schwarzschild's solution wasn't just an answer, it was a key. It opened up a whole new world of possibilities, like a cosmic treasure map that's still guiding us today.
That's a great way to put it. Amazing how work done over a century ago can still be so relevant, so awe-inspiring.
It shows the power of scientific curiosity. A single insight can change how we see the entire cosmos.
Well said. As we wrap up our deep dive into Karl Schwarzschild's world, what's the one big takeaway you want our listeners to remember?
The universe is full of wonders, full of mysteries. There's always more to explore. Just like Schwarzschild, we should never stop questioning, never start pushing the limits of what we know.
Great point. And to everyone listening, if this deep dive got your curiosity going, well, keep exploring. Gravity, space-time, black holes, it's all out there waiting to be discovered.
Keep looking up, keep asking those big questions, and never stop exploring the amazing universe we live in.
That's a wrap on this deep dive. Until next time, keep those minds curious.